Yeah, thank you, Mr. Chairman. Good morning, everybody. I will be speaking about Kinetic Monte Carlo simulations. I'm from University Duisburg-Essen, and if you wonder where that is, I can tell you it's in the very west of Germany, so near the Rhine River. Monte Carlo techniques, or kinetic Monte Carlo techniques, that is, of course, statistical physics. So we continue with statistical physics, and it has many possible applications. For example, you can simulate chemical reactions on the surface, you can simulate protein folding, and in particular, I am interested in simulating crystal growth. So my examples will be from this area. And to give you an idea, here you see a scanning tunneling microscopy of an island on a surface. Say this is indium arsenide and gallium arsenide. And that's technologically important. I mean, these little islands are used as quantum dots in quantum dot devices. And still they are not so small on the atomic scale. So they can be, for example, 30 angstroms long and 30 nanometers long and 20 nanometers wide, so several 100,000 of atoms can be in such an island. And it's deposited from the gas phase atom by atom. But even when you look at a smaller scale, for example, on the surface as such, you see little islands. They consist of atoms or atomic units, and they are elongated. They have a certain density, so all this needs to be understood. And this is related to the growth process. So here we are not studying equilibrium, but we are studying kinetics. There is some temperature, of course, involved, but also there are time scales involved. The time scales with which the atoms arrive on the surface, the time scale for attaching to an island, and that, for example, then relates to the island shape. So in this particular case, if you even look finer, then you see the surface reconstruction of gallium arsenide. So it consists of arsenic dimers that here point into the plane, and gallium atoms. We will see this reconstruction again later on in the talk. So the key point here, many different time scales and length scales involved. Chemical bond making and bond breaking is involved. And this is why we want a first principle description, why we want a DFT description. But at the same time, we need to go to very long time scales, for example, up to seconds, because it requires seconds to deposit such islands, and also to pretty large length scales like micrometers or millimeters. And with conventional techniques, we couldn't do that. I mean, the DFT calculations, they are limited to unit cells that have maybe 10 angstroms or 100 angstroms in size, and you can do ab initio molecular dynamics simulations, for example, up to nanoseconds or a bit longer, depending how powerful your computer is. But in this case, we really need processes that are very slow on the atomic scale. We have activated processes activated by temperature, and these cannot be efficiently simulated by molecular dynamics. One needs some acceleration of molecular dynamics or different techniques like kinetic Monte Carlo. And this is what my talk will be about. But first of all, I would like to go with you through some elementary statistical physics that you know probably from your textbooks, and this first part is about equilibrium. So in statistical physics, people consider simple models. For example, you remember the Ising model of magnetism. You have spins on a lattice, they can point up and down, and there is spin-spin interaction here by the exchange constant. There is the interaction of spin with an external magnetic field. And now you're asking the question, what is the thermal average of magnetization? What is the critical temperature for this magnet, and so on? Or likewise, you can do this in surface physics or in materials physics, where you consider a lattice, a so-called lattice-gas Hamiltonian, where you have lattice sites that can be occupied or empty. So here the variable S maps to a variable C. And again, you can have a Hamiltonian where the occupation of neighboring sites interact. And also here in this case, there is an external field. The role of the external field is played by the chemical potential in this case. So you could simulate the coverage on a surface, whether there is some pattern forming on the surface or not. Or you could simulate an alloy. Is there order in the alloy, or is it a disordered alloy? And all this depends obviously on temperature. So you're interested in thermal averaging. And how is this done? Well, first here I have a model for epitaxy. I mean, also in epitaxy, people use such discrete models where the atoms are represented by little cubes that can move on the surface, and then they can attach, for example, to a step. And in this case, in this simple model, you just have a function h of x, the height, h of x of a lattice. And this represents the morphology of the surface. So there are no overhangs, no voids. And these little cubes, they can move around with a certain rate. It follows an Arrhenius law. And the chemistry comes in by such a simple expression here for the bonding. N is the number of neighbors, the number of bonds an atom makes. And already on that level, you can do some statistical physics of epitaxy. Coming back to the calculation of averages, thermal averages, well, you know, you need to evaluate high-dimensional integrals in statistical physics. And in this case, it's advantageous to use random numbers. You can supply random support points and then evaluate the integral on these support points. And this is actually quite good in high dimensions. The error always goes like 1 over root of the support points, which is a rather advantageous scaling. For example, if you want to calculate the area of a circle, you can play darts. Like here you have a dartboard and then you shoot arrows at the dartboard. So these are your random numbers. And then, for example, 20 arrows hit here a circle, 20 out of 25. So you would estimate pi quarter equals to 0.8. And that's a way of statistical sampling by using random numbers. Now, of course, if you have Ising model or things like that, you want to do it a little bit more sophisticated. You use what is called importance sampling. The density of your sampling points should correspond to the weight of your integrand. Where the integrand in the integral is high, you want many sampling points. Where it's low, you need only few. And there is another idea that comes to it. To create this distribution of sampling points, we use a stochastic process. So it's not an analytical formula or so, but it's a process, a random process, that generates the sampling points according to importance sampling. And a famous example is the Metropolis sampling. Now, if you do Boltzmann theory, as we heard in the previous talk by Sergei, you want to evaluate such a thing here, the Boltzmann factor exponential of minus v over kt divided by the partition function. And this q here, you have to think of it as a variable in high-dimensional space. So positions of many particles, say position of n particles in a gas, or n spins on a lattice or whatever. And this is an interacting system, so you want to evaluate the potential energy. And now to get averages, you can construct a weight function W, and out of your total k sampling points, you have ki points falling into a certain interval in space, and then you can calculate the thermal average of any quantity just by sampling with the number of weight points ki. But now how do we get this distribution function W? Well, there is this Z prime, but actually we don't need to know Z prime. it's sufficient to know that the ratio of two W's here is simply given by the ratio of the Boltzmann factors, and this is the difference of the two potentials. And this relation here actually gives you all you need to generate sampling points. So we generate the sampling points by a stochastic process. We start with some points, and then we generate new configurations, and we either accept them or discard them. So if the energy of the new configuration is such that this exponential here is bigger than some random number, then you accept the new configuration, and if it's smaller, then you reject the new configuration and you try with a different configuration. And in this way we generate many configurations, and then we average the desired observable A over configurational space. The following slide summarizes the Metropolis algorithm in a flow chart. So we start with some configuration, then the configuration is modified by proposing a new configuration. You evaluate the energy of this configuration, and then you draw a random number, you compare this exponential here with your random number, and then you may either reject or accept the configuration. And after a warm-up phase, you can use these configurations to calculate the cumulated average of A. So this is a big loop where you can calculate millions of configurations, and they are distributed according to the weight function W. So you achieve importance sampling by this procedure. I mean, why is there such a criterion? You can easily imagine, I mean, you want to go down to the minimum of the energy. So whenever the energy goes down, you accept the move. But sometimes the energy also goes up. And if it goes up by much, then you reject. But if it goes up by little, then you could still accept it. And this is what you need, because in equilibrium there are thermal fluctuations, and you want to sample the thermal fluctuations. And the Metropolis algorithm gives you exactly the right amount of thermal fluctuations at a given temperature, kT. Now here you always have to reject sometimes, and people don't like to reject. It could be a waste of time. And therefore there are alternative algorithms, the so-called n-fold way. So I explain you what is the n-fold way, and this will also bring us from Monte Carlo to kinetic Monte Carlo. So we will see that time can come into play in this way. First of all, how can you avoid rejecting? For example, if you have a spin system here, you have many spins, and the energy of the spins depends on the neighboring spins. So for example, you could say this is configuration number 3, and 3 is characterized by this middle spin pointing up, and then the left and right spin pointing down. And this configuration 3 occurs just once here. For example, beside you have here configuration 6, middle spin is pointing down, and left and right is pointing up. That would be configuration 6, and this appears 3 times in the sequence. So you have such a coding, and now each particular class of configurations can be associated with a certain rate of changing the configuration. So you want to flip the middle spin, and the probability of doing that is given by some rate. And this is the basic idea of the n-fold way. You make a list of all these classes and how frequently they occur. So 4 times is class 1, 12 times class 2, and 1 time this, 1 time that, and so on. And you sum up and normalize everything by 1. And now you draw a random number. The random number steers a pointer and selects one of these moves. So if the random number points here, then you would execute class 1, and one of these spins falling in class 1 are flipped. And this is the way you generate your new configurations. In this way, you generate each configuration with the right probability, because the thickness of these bricks here is proportional to the probability of doing the flip. So in this way, you don't need to reject anything. You can do the simulation without rejecting. Now doing the step to kinetic Monte Carlo. Kinetic Monte Carlo means time has to come in. In Monte Carlo, we just have simulation steps, but we don't know what is the physical time that belongs to a certain simulation step. Now in Kinetic Monte Carlo, we want to have time, we need time, and of course we need to make sure that each process is executed with the appropriate relative probability to all other processes. If we have these two requirements, correct relative probabilities and correct timing, then our simulation can be realistic. Then we can compare it to an experiment performed in real time. So we need a clock. We need to advance the clock by physical time. Now there is a statement here when this is appropriate, and you need a separation of time scales. Individual flipping processes can be very fast, but then there is a waiting time before the next process happens. And if this is clearly separated, the process itself and the waiting time, then you can say, the waiting times, they have a Poissonian distribution. So I know the distribution of the waiting time, and this can be used to update the clock. And then after you have made a certain move, you need to update the list of all possible processes. There are specific algorithms. That is more or less a matter of computational efficiency. And you will see what it is. It's best understood with an example. Think of epitaxy. You have atoms of a surface. Well, the black atoms, say they form a step, they are not moving. But the red atoms or blue atoms, they are moving. And they can move up or down, left, right. So all these different colors here of the arrows corresponds to a different rate, to a different probability. And say now you want to simulate what these atoms are doing. Well, you could say, I first pick an atom, and then I decide for a move, left or right or whatever. But that's not good. That is actually Foole's algorithm. That doesn't work because you should pick each move with the appropriate probability that is relative to the others, giving the right probability. And that's not satisfied here. What you need to do instead is you need to make a list of all possible moves. Each move has a probability rate gamma, and then you do partial sums. This is the little rk. The total sum is the Rn equals capital R, and then you normalize the accumulated probabilities with the total probability, and then you draw a random number, and as soon as the partial sum exceeds the random number, you decide for this process, for this move. And in this way you make sure that it's the right probability. In this case we need to compare the random number row to many, in the worst case to all these cumulated sums. And this can be inefficient. This is something that needs to be considered when you program the Kinetic Monte Carlo simulation. I should also mention here, for the Kinetic Monte Carlo simulation, you need the total rate R. You need a sum over all possible rates. That's different from the Metropolis Monte Carlo. The Metropolis is simpler in the sense that you don't need to enumerate all possible processes. You just reject or discard. But you don't need to know all possibilities. You just try some possibilities. Sufficient. But here in the Kinetic Monte Carlo, you need to know all possibilities and sum them up. That's the price you have to pay. Now here, this is the way to do it, what I call the process type list algorithm. So you first generate a random number to steer your pointer. It selects you one type of process. So move up or move horizontal or whatever. And then after that, you select an atom that does the move. So in this way, you make sure that the relative probabilities are correct. Now, for example, if the blue has a high rate, you have to select this with a high probability. And you make sure by having this brick large. Now in this process, it's also efficient because you need to compare your random number only once, twice, 3 times, at most 3 times. You don't need many comparisons. Then here I have a flow chart that summarizes the process type KMC algorithm. So we start with some configuration that constitutes the initial state of your system. It depends what it is, what you want to simulate. Then you calculate all rates and the total rate capital R. Then you need 3 random numbers. The first random number is used to select the process type. So you compare this to the partial sums and say if this random number falls in between sum to k and sum to k minus 1, then it means now you have selected process type k. For example, horizontal move. And then you need a second random number to select which atom does this move. That is quite easy, just by taking the integer of this product. And third, now you need to advance the clock. Now this is done by another random number, ln rho 3, divided by capital R. And this ln rho 3 here, this is the Poissonian process. So the waiting time is exponentially distributed, and therefore by taking ln rho 3, you generate an exponential distribution of waiting times. Sometimes these simulations are also called variable time step simulations, because the time step in this simulation can be widely different. Now it's essentially 1 over capital R multiplied by a random number. And capital R is the total rate. So it depends. If you have only slow processes, the total rate is small and the waiting time is long. If you have fast processes available, then the capital R is large and the waiting time could be small. So the time step can vary over many orders of magnitude, and that's the strength of the simulation actually. Now after you have done the move, you need to update the process list. So you need to delete some processes that have become obsolete or add some new processes that now have become possible. And this step actually is computationally the most costly one. So you need to think of a clever way of doing this here. Okay, now I should say all this also has a connection with averaging, with statistical averages. I mean, you can and should do the KMC simulation for many starting conditions. You start, say, 1,000 times with a different seed of the random number generator. And then you get 1,000 movies, 1,000 processes. And if you average over these thousands, then what you get is a solution of kinetic equations. You know, master equation, stochastic differential equations. And this is providing on average a solution of the kinetic equations. That's the statement. There are some details now here concerning how many process types you have. You can either work with some predefined process types, or you can do a self-learning KMC. It has been pioneered by this group here, where you generate the process list on the fly. So if during the simulation a situation occurs where there is some process possible, but you haven't considered that before, you can always add it to your list. Then you need to generate what is the rate for this process. You need to calculate the activation barrier. But in principle, you can add it. So on a lattice, each neighborhood can be classified in a certain way. And these people have made up some coding. And then for each process type, you can calculate the barrier. And in principle, you can have very many different process types. You can have 1,000 process types. And this is then the distribution of the different rates. Also, there are different algorithms. I want to mention there is a different algorithm to do KMC, which is the time-ordered list. In this case, you work somewhat differently. You assign a time to each process. As soon as it becomes possible, you assign a time to this process, and this time is drawn from a Poissonian distribution. And then you sort all processes in a list according to ascending waiting time. And again, this sorting can be done very efficiently. There is a quick sort algorithm that scales logarithmically with the length of the list. So that can be very efficient. And then you simply select the first process in the list that has the shortest waiting time. This is your next process to come. But since it's a random waiting time, it is still, of course, a stochastic algorithm. Yeah? So the advantage here is that this algorithm allows you for the inclusion of any other events that do not originate from the lattice or have some different distribution. Anything that has an assigned time can be added to this list. So that's an alternative when you have very many process types, and the process type algorithm is not so efficient, but the time-ordered list algorithm is more efficient. This slide here points out one frequently encountered problem and its solution in Kinetic Monte Carlo. Now you can have a situation, I mean, this is here a potential, and here you have some minima. And if the particle sits in this minimum, it will jump back and forth many times before leaving this well. So in this time, you get a simulation that looks like this here. In this blue thing here, this is a particle that jumps back and forth many times from left to right, right to left, and so on. And only then it decides to leave the well. So in this case, the Kinetic Monte Carlo simulation is correct, but it's very inefficient. Time advances only very little because this fast process happens many times, but that doesn't advance you very much. Yeah? The solution here is the so-called super bassin algorithm. So you consolidate this triple minimum into a single super bassin. And then, okay, you need a different waiting time distribution. Super bassin can have different exits, and you need different rates for these exits. But all this can be handled. Find it in this publication. And if you do this, then your simulation time advances much faster. You get out of this trap here, and you can simulate 2 seconds, for example, without too much computational effort. Okay, that was the statistical physics part. Now we want to make contact with first principles methods, for example, with DFT. Why and how? Well, in DFT, you have molecular dynamics simulations, Carr-Parinello method, and so on. No? And these are very flexible methods, but if you apply it to epitaxy, for example, then you have exactly this problem that the particle is sitting in one minimum, and it is kind of oscillating in this minimum, and then passes to another minimum, and passes to another minimum. But most time of the trajectory it just spends in a minimum, and that's boring. You waste a lot of computer time just with a particle that sits on its place. what you want to do, you want to use a lattice and simply move the particle on the lattice. And each move here is associated with a certain rate. If you can do that, then you simply cut off this fast time scale of oscillations and you only simulate the move across the barrier. So here there is an energy barrier that you jump over, and this is all you're interested in. You need the rate for jumping over the barrier, and then you can go to the lattice approximation and simulate things much faster. Now this idea comes with a separation of your total system into a relevant part, a system part, and then a heat bath. So the particle here is your relevant system part, but the underlying solid provides a heat bath. And this is where temperature is located, and there is some coupling of your surface atom to the heat bath. And this coupling also determines the expression for the rate. So there is some theory called transition state theory. You can find in this review many things about it, and it comes in different variants depending how strong is the coupling to the bath. Gamma here is the quantity of the coupling, and there is Kramer's rate theory, there is a high friction limit, or there is a medium friction case, and this is actually the case we are considering mostly. So in the medium friction case, your expression from the rate, for the rate, becomes independent of gamma. It only contains here omega 0, the so-called attempt frequency, and it contains the barrier that you have to overcome. So this is the expression that is probably familiar to you. In case of weak friction or strong friction, you have somewhat different expressions. But I don't go into the details here. I only want to tell you if I have a multi-dimensional case, then you can also handle this. You need to consider this. For example, if a particle is wandering on a multi-dimensional potential energy surface, then you also have barriers. You can calculate the barriers from minimizing the total energy. And then your expression for the rate must also account for the multidimensionality of the problem. So in this case, the transition state theory tells you that the rate can be expressed as a ratio of two partition functions. Zi is the partition function when the atom is sitting in minimum I, and Zts is a constraint partition function when the particle is sitting at the saddle point between the minima, and it's constrained to sit there. It's not allowed to fall down in the minimum, but only move perpendicular to the reaction path. Now if you make further approximations like harmonical and classical approximation, then this expression can be broken down into such an expression here where you have again an exponential with a delta E, the energy difference between initial state and saddle point, and you have a prefactor that is given by the ratio of two products, the product of all normal mode frequencies in minimum I, and the product of the normal mode frequencies at the transition state. Now this is a constraint to directions orthogonal to the reaction coordinate. So it's n-1 modes you have here and n modes in the minimum. And that's why this gives you an attempt frequency. So this is often used, but it's also based on approximations, and one can go beyond these approximations if desired. I would like to show you a somewhat different method here, a detour, a method that you can also use if you're not happy with a lattice approximation. If your atoms are not sitting on the lattice, then you can still do molecular dynamics, and you can do temperature accelerated molecular dynamics. So in this method, you're not using any particular stochastic theory, you're just simulating your system by molecular dynamics. But in order to speed up the simulations, you need a higher temperature. You use a higher temperature because then everything will happen faster. But of course, your prediction has to be for the low temperature. And then you are using transition state theory to scale down from the high temperature to the low temperature. So you're using that the rate law has this exponential form, and this allows you to scale down from the rate at high temperature to the rate at low temperature. And then you can do the MD simulation. It will give you some processes. After you have found so and so many processes, you stop, because you can have an estimate that no new processes are likely to occur after a certain time. And this gives you here then the rates of the processes at high temperature, but also at low temperature. And then you can use these rates to do a stochastic selection, to select one process with a rate belonging to the low temperature, and then do a Monte Carlo move. So you use the high temperature MD simulation to fill your process list, and then scale it down to low temperature and select according to the low temperature, which is quite smart, I think. And even this method, it allows you to study concerted processes, for example here in crystal growth. People found that there is a process, for example, where an atom climbs down from an island into the lower layer, and this is a concerted process where many atoms participate. So it's more demanding to model. But also this technique allows you to use parallel resources efficiently. I mean, whenever your simulation gives a jump of an atom, you can spawn a new subtask. For example, you have a processor 2 that follows the system after the jump. And at the same time, you have the processor 1 continuing, so it may generate an alternative jump, or even another alternative jump. So each jump of the system gives you a spawning of the task, and this keeps another processor busy. And after you have collected so and so many possible processes, then you do the Monte Carlo selection based on the downscaled rates. So you select one process, and at that time the other processes become obsolete, so you stop the simulations. This is why it's called speculative TAD. You only use these parallel processors in case this process is selected. If it's not selected, you just discard them. But this allows you to speed up the TAD method considerably. And here you see an example from Art Voter and his group. Here they simulated copper on silver, and they simulated deposition of one monolayer on the parallel machine within 9 hours. And I mean, Art Voter is here making the point, if you had done this simulation in 2002 with a serial TAD algorithm, it would have taken you 1 year. So the spawning of tasks gave a big speed up of the simulation. Still, of course, any such TAD simulation is much slower than a lattice KMC. If you can do a lattice KMC, then you should do it. It's much faster. Okay, this was the method part. Now I would like to show you some examples. These islands here on the gallium arsenide surface, this is some example I studied a couple of years ago, actually. Now in gallium arsenide you have two components, gallium and arsenic, and they are both offered from the gas phase. So you have deposition of gallium atoms, deposition of arsenic molecules. People work actually with a high surplus of arsenic, so most of the arsenic desorbs again. we also need to include desorption of arsenic. And then, of course, you have a diffusion of the atoms on the surface, diffusion of gallium, attachment of gallium to islands, growth of the islands. And the crucial point here is the interplay of all these processes. If you only had one species or only 2 or 3 processes, it would be easy. But in epitaxy, you have an interplay of many processes. And some processes only become possible after an island has nucleated or after something has happened. This makes it difficult to foresee things, and this is why a computer simulation can help you in this respect. So here again, we calculate barriers. For example, the yellow atom here is a gallium atom, and it can sit here on the surface in this state, or it can insert itself. You see here that there is an arsenic dimer, and it breaks the bond and inserts itself in the arsenic dimer, and then is more stable. And this is then the transition state, so I calculated this barrier for inserting, and many other barriers I calculated. For example, for the diffusion of gallium, we consider a potential energy surface. So the grayscale here shows the depth of the minima. There is a very deep minimum for the gallium sitting here in the arsenic dimer, but it can also sit here in between, or it can sit up here. And then you have jumps. It can jump, say, from here down into the trench or up into the mountains. So the diffusion here consists of many different moves. But all this complexity can be incorporated quite easily in the Monte Carlo simulation. So from the minima and from the barriers, we derive the activation energies and we derive the rate constants. And then we can do a process type KMC simulation. One thing to realize here is that the Kinetic Monte Carlo simulation, it always builds on a classification of processes and a classification of environments. In the simplest case, as was pointed out here already in the 80s, you could just look at the occupation of neighboring sites. Now, if this red atom wants to make a move, then you could say how many neighboring sites are occupied. And the rate depends on this local occupancy. And whenever this situation occurs anywhere on the surface, then you say, aha, it's this class of process, and it has this rate. So you use the same rates over and over again because the same local environment occur many times on the surface. And in gallium arsenide, it's the same with some modifications. For example, this atom here has a neighbor, and then its probability of moving will be different. It is modified by the presence of a neighbor. Here we have a chain of 3 atoms. Now the probability of breaking away is modified by the presence of neighbors. This is essentially what you need to take into account, and this defines your process types. So in this simulation I had 32 process types, 32 different processes, and they have quite different barriers. For example, arsenic desorption has a quite high barrier. Gallium diffusion has different barriers depending on the environment. It can be low or high. And all these processes happen at the gross temperature of about 850 Kelvin. So all these processes should be allowed and should be taken into account. And this defines the challenge here. We can take a simulation cell that is quite large, could even be taken larger, and we need to consider large time scales up to 10 seconds. But with the KMC we can do that because of this variable time step in the KMC algorithm. And now here you see the example, you see the reconstruction of gallium arsenide. It has trenches with arsenic dimers in the trenches. So here the blue things are arsenic atoms, and the green things are gallium atoms. And now you will see new gallium atoms arriving and arsenic atoms arriving, which are shown in yellow. Gallium is shown in yellow. This movie only shows a small part of the simulation cell, and it only shows time steps of milliseconds. Of course, some time steps are much faster, and this is why there is a lot of blinking in the situation. So you see here some blinking. Now gallium has arrived already. It splits the dimers that are here in the trench. So this island advances here. And as it advances, also there are arsenic molecules arriving. These are the new arsenic molecules, and they fill the trench, but they also absorb in a new layer, and the island grows into a new layer. So this blinking here, this is reversibility. The atom can attach or detach, and it does this on a very fast time scale. So in the movie it appears as a blinking. And here you see now an island that has grown after 1 second. And to compare to experiment, we analyze the island density. So here you see the same simulation on a coarser scale. And you should see a movie, but it's not. Here now it's proceeding. So you see islands that grow along the trenches, and then this yellow pixel here, this is when the island goes in the second layer. And here you see the island density as it increases in the course of time. And this is shown here for different temperatures. So the island density saturates at some point. This is mainly because you have attachment. So when an atom arrives somewhere, it diffuses on the surface, and then it attaches to an existing island. And only if it doesn't find an island, then it may find another atom and nucleate a new island. But if you have already reached a certain island density, then no more new islands are nucleated. The old islands capture all the arriving atoms. This is why it saturates. And you see that the saturation value depends on temperature. Monotonically, but not quite. I mean, here you see at 880, the island density increases again over 800. So one can put this island density in an Arrhenius plot. This is what you do in this field. You have here the logarithm of the island density. And here you have 1 over temperature, or 1000 over temperature. And then the simulations give me this curve here of the island density. So when you raise the temperature first, the island density decreases. This is because the atoms diffuse faster. So they reach the existing islands very easily, and you need only very few islands for saturation. But then here there is a turning around. At high temperatures, the island density increases again. And this is because you are running short of arsenic in this region here. Above 800, the arsenic desorption becomes appreciable. And the arsenic, it acts like a glue. It keeps the islands together. So when you lose too much arsenic, then your islands become fragile and you get many small islands. Now the experimental conditions you see here, we only have 1 point because experiment is always done at 850 Kelvin. This is the temperature that gives the best results technologically. And here we are on this rising flank, so you have just enough arsenic to provide the glue, so to say. There are also simpler theories, analytical theories of island nucleation, which are shown here, but they only give you such a monotonic dependence here, where the slope of this dependence is given by the critical nucleus. So I have a brief second application, sintering. This is also an interesting process. I mean, some materials cannot be grown from the melt. Some alloys cannot be grown from the melt. You can only prepare powders, and then you compactify the powders. You use temperature and pressure to create a solid material out of it. Here, for example, you see iron that was produced from iron tetracarbonyl. It consists of these little small balls here, which are then compactified. In this compactification process, it is also a kinetic process. So the particles grow, and large particles eat up small particles. And this is something that can be simulated by molecular dynamics combined with kinetic Monte Carlo. So in this case, you have particles. They can attach and move, for example, rotate as rigid bodies. But at the same time, these particles have crystal facets. The atoms can diffuse on the facets, and this leads to the formation of necks. So the particles grow together, and this is the microscopic physics of this compactification or sintering. And this was a simulation done by colleagues at University Duisburg-Essen, compactification of powders. Okay, with this I come already to my summary. I mean, what you should take from this lecture is basically you have a wide range of methods. Some are very accurate, need little input. For example, molecular dynamics or accelerated molecular dynamics can be done without too much interference with the user. Some methods are very fast and simple, but in this case, there is the risk of oversimplification. You have to decide whether this method is appropriate for your solution. Some methods are intermediate. So essentially, it's a trade-off between computational effort, where MD is highest, and the risk of oversimplification or the risk of omitting something important, which is clearly there in these lattice methods. But still, for many cases, like what we saw for gallium arsenide, such a lattice KMC with the n-fold way is a very attractive method and can give you important insights. So I would say you should keep things as simple as possible, but not more simple. And this is a quotation by Albert Einstein. So with this, I thank you for your attention, and I am happy to take questions.